Hello everyone, I am Zhang Jinduo from Beijing Institute of Technology. It is a great honor to participate in this meeting. The subject of this report is Channel Estimation for Millimeter Wave MIMO System, a sequential analysis approach. This report is divided into 5 parts, namely motivation, problem formulation, algorithm design, performance analysis, and conclusion. Now let's go to the part 1, motivation. At present, the scarcity of spectrum resources and high throughput capacity restrict the development of wireless communications, and the millimeter wave MIMO system is a solution. The millimeter wave has the characteristics of short wavelengths, rich spectrum resources, and severe fading, while the MIMO multi-antenna system can compensate for the defects of the millimeter wave. The millimeter wave MIMO system can make the spectrum resources rich, increase the channel capacity, and increase the signal-to-noise ratio. The frequency band of millimeter waves is shown in the figure. There are 3 main characteristics of millimeter waves. The first is that the wavelength is extremely short, which means the frequency is extremely high. The second is that the bandwidth is very wide, and the third is that the fading is severe. Multiple input, multiple output technology, abbreviated as MIMO technology. Its multiple antenna structure is shown on the right. Its advantages include high spectral utilization, high link reliability, and huge coverage. In wireless communication, channel estimation is an important step and a prerequisite for high-throughput information transmission. However, using traditional methods to perform channel estimation in a millimeter wave MIMO system will cause excessive time overhead. The experimental facts points out that the millimeter wave MIMO system has the characteristics of fewer scattering paths, and the scattering angle changes much slower than the coefficient changes. Therefore, this study mainly uses these characteristics to design a new channel estimation algorithm to reduce time overhead. Next is part 2, problem formulation. By taking use of the features of millimeter wave MIMO system, which include few scattering paths and angle changes much slower than coefficient changes, we are required to overcome the shortcomings of existing algorithms and design low signaling overhead algorithm. The key points of the procedure are algorithm design and performance analysis. The structure of the transmitter and the receiver in this study is shown on the upper right, and the channel expression is shown below. It can be seen from the expression that the channel is determined by the scattering coefficient and the scattering angle in the scattering path. The scattering angle is further divided into angle of departure, AOD, and angle of arrival, AOA. These are the concepts that we'll mention later. Then we come to the part 3, algorithm design. As mentioned earlier, we mainly use the features of the millimeter wave MIMO system that there are no more than 3 scattering paths and the angle change is much slower than the coefficient change for solution design. Generally speaking, in each fading block, the object to detect the change is the scattering angle. When the scattering angle does not change, the channel coefficients can be estimated with very few samples. When the scattering angle changes, we use traditional methods like OMP to re-estimate the angle and the coefficients. Specifically, in a fading block, channel estimation needs to be performed before the transmission of information is officially started. The angle change is divided into 2 possible situations. disappearance and appearance, and these two situations are detected separately in chronological order. The detection process is divided into two steps: design and make decision. Design refers to the design of precoders and combiners that match the disappearance and appearance conditions respectively. Make decision refers to make a decision on the occurrence of these two situations. The figure shows the entire detection process. It can be seen from the figure that the detection is performed in a fitting block. Before the detection starts, the current existing angles are known. The detection process is divided into four parts. Process 1 and Process 2 are for angle disappearance, and Process 3 and Process 4 are for angle appearance. Process 1 to 4 are executed in chronological order. Specifically, Process 1 is to design the precoder and combiner for the disappearance of the angle, and Process 2 is to determine the disappearance according to the design of the Process 1. If it is determined that the existing path disappears, the angle and the coefficient will be re-estimated, and then the information will be transmitted. Otherwise, if it is determined that the angle remains unchanged, Process 3 will be executed. Process 3 is to design the precoder and combiner for the angle appearance situation, and Process 4 is to determine the appearance according to the design of Process 3. If it is determined that a new path appears, the angle and a coefficient will be re-estimated, and then the information will be transmitted. Otherwise, if the path is determined to be unchanged, the coefficients will be estimated with a small number of samples, and the information will be formally transmitted. This is the flowchart of the whole process. The specific flow is as mentioned before and also explained. In comparison, the traditional channel estimation method requires a large amount of signaling overhead due to the need to detect changes in both angles and the coefficients. However, this method only needs to detect the angle change, so that the overhead in our detection process is less. Next, the system model and the problem description are shown. The block diagram of the transceiver is shown in the right figure, and the channel expression is shown in the lower right corner. The symbols and the formulas used in the research are also listed on this page and the next page. Some important representation include vectorization of the channel matrix, received signal Yk, precoder vector Vk, and the combiner vector Wk. The expression of the received signal is shown below. From the expression H can be estimated from Yk by designing Vk and Wk. Next, we will design for the disappearance of the scattering path, which is expressed as Process 1. The set of all possible scattering paths is denoted as P, and one of the current existing paths is P star. The design problems of the precoder and combiner are as follows, which are Problem 1 and Problem 2. Problem 1 and Problem 2 are non-convex problems, which are hard to solve. Fortunately, research shows that when the rank of the solution is 1, it can be transformed into a semi-definite programming (SDP) problem in convex optimization. Some of the required definitions are shown below, and the purpose is to convert Wk and Vk into matrices. As mentioned before, Problem 1 and Problem 2 are equivalently transformed into the following problems, which are Problem 3 and Problem 4. Problem 3 and Problem 4 can be solved by simulation tool, and then the following algorithm can be used to convert the rank of the solution matrix to 1. The problem form required by the algorithm is as follows. which is consistent with the form of problem 3 and problem 4. The specific process of the algorithm is shown on the right. The key is to obtain an equivalent matrix with a gradually decreasing rank through continuous iteration until the rank of the matrix reaches 1. Through this algorithm, the solutions of Vk and Wk can be obtained. Next is the determination process for the disappearance of the scattering path, which is process 2. The Vk and Wk obtained in process 1 are used, and the received signal sequence Yk is already known. When the angle disappears, assume that its occurrence time is tau1, then before tau1, the path P star exists. Yk obeys the complex Gaussian distribution, and its mean and variance are shown, and alpha n also obeys the Gaussian distribution. The mean and variance are also shown. After tau1, the path P star disappears, and Yk obeys another complex Gaussian distribution, with its mean and variance as shown. It is required to determine the disappearance with a small delay and a low probability of false alarm. After comparing a large number of different algorithms, it is found that the efficiency of Q-sum algorithm is relatively highest. Therefore, the cumulative sum algorithm, that is, the Q-sum algorithm, is used to make the determination. The basic definition of the Q-sum algorithm is as follows. It can be found by definition that the core of the Q-sum algorithm is to determine whether the cumulative sum exceeds the set threshold. The next design process for the appearance situation of the scattering path is process 3. The difference from process 1 is that in process 3, the discretized AOD is divided into uniform sectors, and one sector is scanned at a time, while for AOA, omnidirectional scanning is performed. When the detector determines that there is no path corresponding to the current sector, it will turn to scan the next sector. The AOD set of scanned sector is NDI. Then the design of the precoder and combiner are as follows, namely problem 5 and problem 6. Similar to problem 1 and problem 2, problem 5 and problem 6 are equivalently transformed into STP problem, that is, problem 7 and problem 8. After the solutions of problem 7 and problem 8, which are solved by the simulation tool, the following Gaussian randomization algorithm can be used to convert to the rank of the solution matrix to 1, thereby obtaining the corresponding Vk and Wk. Different from the process 1, which reduces the rank of the matrix until it reaches 1 through iteration. The key of this algorithm is to directly generate a feasible solution of rank 1 through the Gaussian randomization process. Next is the determination process for the appearance of the scattering path, which is process 4, by Vk and Wk obtained from process 3, and the signal sequence Yk is known. There is time tau 2. Before that, path P star doesn't exist. Yk obeys rise distribution. After tau 2, path P star appears. Yk obeys another rise distribution, and the appearance of new AOA and AOD will be detected separately. The distribution and the parameters of Yk before and after tau 2 are shown in the figure. The Q-sum algorithm is also used for detection. Next is part 4, performance analysis. Here is the parameter settings, including the number of antennas, wavelength antenna, spacing, and so on. And here are the relationship between time delay and the threshold in figure 1, and the relationship between false alarm and the threshold in figure 2. Here is the comparison of QSUM and binary detection in Figure 3. We can see the performance of QSUM is better than binary detection. Finally, here is the comparison of current method and OMP method in Figure 4. It can be seen that in the different SNRS, under the same NMSE, our method spent less time overhead than the OMP method. Here is the final part, Part 5, Conclusion. We propose a method of channel measurement for millimeter MIMO system based on the fact that the AOD and AOD coherence time is much longer than the one of channel coefficient. To realize our idea, we utilize the QSUM method to detect the variation of AOA and AOD with low time delay, which falls into the area of sequential analysis. To enhance the performance of QSUM, we design beamforming for both the precoder and combiner. Through SDP, optimal or suboptimal solution can be achieved for the formulated beamforming problems. The simulation results shows that when the same effect is achieved, our algorithm reduces the time overhead compared with the traditional OMP algorithm. Our proposed method can help to save the signaling overhead for the channel estimation. This concludes the report. Thank you, everyone.